welcome. As we were teaching Gauss-Bonnet this week in Math 136, differential geometry, we have proven in detail the local Gauss-Bonnet theorem and the global Gauss-Bonnet theorem. I wanted to say a little bit more about the general Gauss-Bonnet theme. It's a whole panorama. Let's just start here with one, the triangle. The earliest occurrence of Gauss-Bonnet is adding up angles in a triangle, and you can see that as adding up the complementary angles, which are curvatures, and this can be generalized to polygons, and these exterior angles or these complementary angles are curvatures, changes of the angle, right? You change the angle, you add up all these angle changes, you get 2 pi, and this also kind of becomes the Hopf Umlaufsatz. When you have a simple closed curve, you can look at the change and you can integrate up the curvature, and what you get, curvature needs the second derivative, so that uses C2. You can also have a Gauss-Bonnet theorem here. If you are on a surface, that works too. If you have a polygon on a surface, on a sphere, for example, you can add up the curvatures, but then there is also the interior curvature that comes in, and then the formula here has been shown in the 1500s, in the 16th century, by Harriot or Girard, and a little bit later also in the hyperbolic case, when you have negative curvature, or like here, curvature constant -1. But that's all part of this local Gauss-Bonnet result here, which then adds up. You can cut up a manifold into pieces and you get the global Gauss-Bonnet result. Maybe something which is going beyond it is if you look at the convex curve, which doesn't need to be smooth. It doesn't even need to be differentiable. But what you can do is, you have a convex curve, you have a measure, Choquet measure on the boundary. You can define an angle, a function f, which is like a integrated density of states, or CDF in probability theory, which grows. So this can be a polygon also. In a polygon it would be just piecewise constant. And what happens then in a polygon, you would have point measures. So Lübeck showed every measure can be written as this is a point measure. That's where you have corners. Singular continuous, that's the interesting case. Also, then we have the absolutely continuous case. That's the place where you have almost everywhere differentiability. So that works also, and this is kind of more a probabilistic story, that you can see this as a Gauss-Bonnet result. So Gauss-Bonnet here is actually just that the total probabilities is 1. So if you have a general curve, a Jordan curve already, that can be very complicated. Jordan curves can have positive measure even, and so it can be very complicated. And there to have a Gauss-Bonnet would be much more difficult, because but you still could kind of attach a measure on the boundary, integrate that up, and have interpretation of a Gauss-Bonnet result. We also covered kind of in a homework this Descartes result, which is very, very beautiful. So if you have a polyhedron, and you can kind of look at the excess angle. When you look at the excess angle in a cube, the excess angle is 2 pi minus 3 times pi half, which is pi half at every corner. So you have pi half times 8, which is 4 pi. So that's something Descartes already saw, and that's a beautiful also version of Gauss-Bonnet. You attach curvatures to the corners, and you can see that also probabilistically as an expectation, index expectation of Poincare-Hopf. So you embed it into R3, you take functions which are linear in the ambient space, and you look at the indices, so look at maxima, minima, and then you can look at the probability that this happens, that you have a maximum. So you get the curvature, which is exactly that curvature here. So yeah, that was the topic we have covered. We have also covered at least in 2 dimensions, the discrete version. You can attach curvatures to a discrete manifold, which is there's a general formula for it. In the case of a nice two-dimensional manifold. It's just 1 minus the number of the vertex degrees divided by 6. So it's a nice curvature which adds up to Euler characteristic. But it's in very general. It's for every network you have that. You have also for every network you have a Poincare-Hopf result, and you can see curvature as an expectation of these indices. So that's more general. This allows you to define more general curvatures on a manifold or more general curvatures on a network. It's kind of a unifying theme. I should also mention the higher dimensional version of Gauss-Bonnet for even dimensional manifold, compact manifolds. There's a curvature here which Hopf already looked at, and so Hopf looked at hypersurfaces in ambient space, so codimension 1 surfaces, and that this has been then generalized more and more, and eventually Chern was giving an intrinsic proof in the 2n-dimensional, 2k dimensional manifold. But this is the Riemann curvature tensor, which we actually are going to look at also in 136. We also, this is going beyond the course, proving that is not easy. Okay, so that's what I wanted to say today.